We have almost covered chapter 4, and this is probably the last lecture on chapter 4, where we'll look into few of the numericals and certain portion that deal with the specific heat of liquid and solids or incompressible substances, and the internal energy and enthalpy related to these phases, solids and liquids. So before we move on towards solids and liquids, let us have a look at few of the numeric. Now, this is one of the numerical which states that a piston cylinder device, it initially contains 0.5 meter cube of nitrogen gas at 400 kilopascal and 27 degrees centigrade. An electric heater within the device is turned on and is allowed to pass a current of 2 amperes, uh, 2 amperes for 5 minutes, and 120-volt source is being used. It says that nitrogen expands at constant pressure. So the pressure at which the expansion is taking place is constant, and at the same time there is a heat loss of 2800 joule that occurs during the process. You have to determine the final temperature of nitrogen as a result of the process that has taken place. Now let us have a look at the schematic of the process. So this is a closed system. The system is closed. You have nitrogen gas in the system, and you can assume this gas to be an ideal gas. The pressure of the pressure, volume, and temperature at the initial condition are given to you. These three are the pressure, volume, and temperature. And as the electrical work is being done on the system due to resistive heating, uh, there is some boundary work associated with the movement of this movable boundary or piston, and at the same time there is some heat which is being lost due to the surroundings from the system. This is the information given to you. You have to determine that what is the temperature at the final state of your system as a result of this heat loss, the electrical work in, and the boundary work associated with these two energies. So the information given to you is that you have electrical work that you can calculate using the Vi delta T equation, voltage multiplied by current multiplied by the time in seconds would give you the energy in joules. And if you divide this by 1000, it would give you the total energy in kilojoules. This is the electrical work that has been done on your system on the closed system. Now, if you know the electrical work, we'll be slowly moving on towards the energy balance equation. Before we move on towards the energy balance equation, is there any way we can find out the mass of the system?
सर वॉल्यूम दी हुई है, प्रेशर दिया हुआ है, तो स्पेसिफिक वॉल्यूम से हमें पता चल सकता है।
स्पेसिफिक वॉल्यूम कहाँ पे?
सर नाइट्रोजन की क्या होगी 400 किलो पास्कल पर।
सर
You
वो
are
नाइट्रोजन
considering
की
पीवीआरटी आइडियल गैस चीज
नाइट्रोजन की जो सर वो वॉल्यूम गिवन है और डेंसिटी हमें उसकी मालूम है।
No, you will use the I have mentioned the word ideal gas. The ideal gas equation PV equals to mRT. This is the equation. Pressure is given to you, volume is given to you, temperature is given to you. I have already mentioned that the gas constant R for different gases, it is mentioned in the tables at the back of your book. So you can find out the R constant for nitrogen, and that would give you the mass at this condition. So if you look at the equation, this is the sorry this is the pressure given to you in kilopascal. The volume is known to you. The R, which is the gas constant, can be found out from the tables at the back of the book for nitrogen. and temperature is known to you. You have to plug in the temperature value in Kelvin. This would give you the total mass of your system. Is it clear?
Yes, sir.
All right. Furthermore, now you have to apply the energy balance equation. Energy balance equation for a closed system is a simple equation, which is basically E in minus E out equals to change in energy of the system. And change in the energy of the system, you will come to know that since it's a closed stationary system, you can replace it with delta U system. So you have essentially this equation, E in minus E out equals to change in energy of the system, and you'll replace the change in energy of the system with delta U of the system since it's a closed stationary system. Uh, Catering for the energy coming in and energy going out, you have basically the energy which is coming in is essentially the electrical energy which is coming in. The energy which is going out is Q out, heat which is flowing out of the system, and the boundary work which is due to expansion of your piston. This is essentially equal to delta U of your system. So if you look at the equation, this is your equation for the specific system that has been defined in the statement. Now electrical work in you have calculated, Q out is known to you. You already know from your knowledge that for a system which is undergoing a constant pressure expansion or contraction or compression, you can combine boundary work in delta U with delta H. And delta H is all you already know is nothing but if you remember DH is essentially MCP dt. This is DH. So if we have MH2 minus H1, which is DH, DH can be replaced by CP T2 minus T1. Mass is already there. Now, if you look at this equation again, these two values are known to you. Mass is known to you. T1 is known to you. CP is something that you can find out from the tables for nitrogen as the ideal gas, and T2 is what you have to find out. So if you plug in the values, CP value for nitrogen from the table A2 is 1.039 for room temperature, since you are already at room temperature. And if you plug in the values, you will have the T2 value to be 56.7 degrees centigrade. Is it clear?
Yes,
Yes,
sir.
sir.
All right. Moving on, you have the second
सर
example. GG,
एक्सक्यूज मी सर एक्सक्यूज मी
जी.
सर ये बहुत से एग्जांपल में हमें ये स्टेशनरी क्लोज सिस्टम का बताया नहीं गया होता है तो हम ये एज्यूम करेंगे.
Yes, unless the system is moving with regards to elevation or with regards to velocity. If there is no information given about the system, the whole system moving with regards to some reference point in terms of elevation or in terms of velocity, you will assume your system to be stationary if it's a closed system. अगर आपके पास एलिवेशन की चेंज होने की और वेलोसिटी के चेंज होने की सिस्टम की बात करूं एज ए कंप्लीट सिस्टम इंफॉर्मेशन नहीं है तो यू विल ऑटोमेटिकली अज्यूम योर सिस्टम टू बी ए स्टेशनरी सिस्टम.
ओके सर थैंक यू.
क्लियर?
यस सर.
So you have another example which says that a piston cylinder device initially contains air at 150 kilopascal, 27 degrees centigrade. So this is the fluid that is being part of your system. At this state, the piston is resting on a pair of stops as shown in the figure, and the enclosed volume is 400 liter. So your P1, T1, and V1 they are given to you, and other than that, the information given to you is that there is a piston which is resting on these two stops. So the piston cannot move downwards. This is what you understand by uh, the statement that says the piston rests on the two stops. Now, it is further said that air is now heated until its volume has doubled. There is some heat addition to the system, which ultimately results in the volume of the system getting doubled. And before that, it says that mass of the piston is such that a 350 kilopascal pressure is required to move it. So it says in order to get to the double volume, where your volume essentially doubles, there is a pressure which is required. So your pressure needs to has doubled, you have to find the final temperature, the work done by the air, and the heat that has been transferred to the air, which is causing this change in volume. Now, the first assumption that I'll go for is that since it's air, I'll assume the pressure as low and I'll assume that it's as an ideal gas. This is the first assumption. The second most important assumption is that this expansion process is taking place at a constant pressure of 350 kilopascal. Since I don't have any other information, I'll assume that the piston starts moving at 350 kilopascal and continue moving at 350 kilopascal until my volume basically doubles. Clear enough?
Yes,
Yes,
sir.
sir.
Furthermore, I would assume again the system to be stationary closed system. So if I have to determine the final temperature, these are a few of the assumptions which is related to this system, and the assumption which is valid is that there is no electrical shaft or other forms of work involved in the process other than the movement of the boundary WB. There is no other work involved in the process. Now, if you have to find out the final temperature and you have assumed air to be an ideal gas, if you look at the conditions P1, V1, and T1, they are known to you. These are known to you. The pressure, which is the final pressure, the volume, which is the final volume, these two are also known to you. And you have to find out the final temperature. The final pressure is essentially 350 kilopascal, the constant pressure at which your piston moves. This is an assumption. We have taken this assumption since there is no other information given. The final volume is essentially twice that of initial volume, and you have to determine the final temperature. For such a case, you know the ideal gas equation. How can we find out the final temperature?
सर पी वी इक्वल टू सर दोनों जो दो इक्वेशन इनिशियल और फाइनल के लिए जो आइडियल गैस इक्वेशन आएगी उनको इक्वलेट करेंगे.
Very good. So you know that for ideal gas having two different states, you essentially have P1 V1 over T1 is essentially equal to PF VF over TF. This is the equation. So in this equation, the only thing unknown is the final temperature TF. So if you apply the equation P1 V1 over T1 is equal to P3 V3 over T3, you would essentially have these values. The initial volume to you, the initial volume is known to you, the initial temperature is known to you. The final pressure is known to you, the final volume is twice that of initial volume, and T3 or the final temperature is not known to you. Why we have used this third state, not the second state, we'll come to that in a minute's time. Why we have used this once we draw the PV diagram. T3 basically comes out to be 1400 Kelvin as a result of this process. Clear enough? So far, is it clear?
Yes, sir.
All right. Now, moving on, let us have a look at the PV diagram. Now, This is the process diagram or PV diagram for the statement that has been defined for you. Your initial condition was where your initial pressure was 150 kilopascal and your volume was zero point 0.4 meter cube. In order for the piston to move, you had to supply some heat and you had to raise the pressure from 150 kilopascal to 350 kilopascal. Unless and until your pressure gets to 350 kilopascal, the piston would not move. So the first process was due to the addition of heat, your system, the pressure inside increased from 1 to 2 to 350 kilopascal. Once the pressure has reached to 350 kilopascal, the second thing was the expansion at constant pressure from 3 to at 350 kilopascal until and unless your volume doubles to state 3 where your volume has changed from zero point 0.4 to zero point 0.8 meter cube, and this has taken place at constant pressure. So this is the process diagram. Now if I have to calculate the work done by the air which is there inside the system, how can I find out the work done by the air?
सर 1 to 3 एक लाइन ड्रा कर लेंगे जो इसके नीचे ट्रेपेजियम होगा वो वर्क डन बाय द एयर होगा.
Why 1 to 3? This whole area is representing the work done by the air. This whole area is essentially the work done by the air. You are going from process 2 to 3. The whole area is due to the work done by the air on a PV diagram. It's simply, if you remember, boundary work is essentially equal to PdV, and if your pressure is constant, it is simply P into V2 minus V1. Your pressure is constant, which is 350 kilopascal. Your volume change is essentially zero point 0.4 meter cube. So zero point 0.4 meter cube multiplied by the pressure would essentially give you the work done, total work done. It would be in kilopascal, so it could, you can write it as meter cube dot kilopascal, or it is the same thing as kilojoules. Is it clear to you?
Yes.
सर ये एयर
Yes, sir.
इनसाइड द सिलेंडर की बात हो रही है.
जी, और कौन सी एयर वर्क कर रही है?
सर वर्क डन वो जो अगेंस्ट वेट ऑफ द पिस्टन करता है ये वही होगा ना.
जी बिल्कुल ये वही होगा.
सही, थैंक यू सर.
All right. So once you know the work done, the third thing is you have to determine the heat supply to the system. In order to determine the heat supply to the system, you have to apply the energy balance equation, which says E in minus E out equals to change in energy of the system. Now, in this case, again, the delta E of the system, you will replace it with delta U since you to have a stationary closed system. And in terms of energy in and energy out, you have to find out the energies which are coming into the system, energies which are moving out of the system. So essentially, you have Q in, which is being supplied to the system, boundary work, which is due to the expansion of your system. It is equivalent to delta U, or it is equivalent to mass multiplied by specific enthalpies of air at 300 Kelvin and 1400 Kelvin. So Qn is something you need to find out. Boundary work you have already determined to be 140 kilojoules. How can we determine the mass of my system?
सर इंथैल्पी से हम वो स्पेसिफिक वॉल्यूम फाइंड कर लेंगे, वॉल्यूम मल्टीप्लाई मास कर लेंगे टेबल से.
Beta, again, we have assumed air to be ideal gas. When you have ideal gas, your pressure, volume, and temperature are known to you. Remember that for an ideal
Ideal gas.
gas, mass is P1 V1 over RT1. R is the gas constant for air, which you can find out from table A2A. You just have to plug in the values 150 kilopascal, volume, temperature in Kelvin, and this is your R gas constant for air as an ideal gas, and that would give you the mass of the system. Once you have the mass of the system, how can you determine the internal energies U3 and U1 for air as an ideal gas? This 3 is essentially 1400 Kelvin and U1 is essentially 300 Kelvin. Again, we have looked into three ways to find out the internal energy or DU for an ideal gas. Air is an ideal gas, and the easiest thing is to go to table A17 for air, and you can find out that for air, U at 300 Kelvin is 2134.07, and for 1400 is 1113.52. You just have to plug in the values, and this would give you the total heat which is being supplied to the system. Clear enough?
Uh, yes, yes, it's clear.
All right. So moving on, we have now the topic of internal energy, enthalpy, and specific heat of solids and liquids. We have to relate the internal energy, enthalpy, and specific heat for solids and liquids. One thing which is associated with solids and liquid is that they are incompressible. That means their specific volume or density is independent of the pressure, it remains constant. G, any question? All right. So, if you're talking about liquid and solid, and their incompressible, specifically their specific volumes would remain constant with regards to pressure. Another thing associated with solids and liquid is that you don't have two different kinds of specific heats. Specific heat with regards to constant volume or constant pressure is essentially same for solids and liquid, and it is defined by the term C. So C value, which is the specific heat for iron, is the amount of energy required to raise the temperature of iron by 1 degree for a mass of 1 kg. It is the same for constant pressure and constant volume, so it's essentially represented by the letter C for solids and liquids. Now, moving on, when you have to determine the internal energy changes for solids and liquids, the internal energy equation is essentially du Cv dt for the gases. Cv dt is replaced by Ct, specific heat having a relation with temperature for solids and liquids. Since there is no Cv and Ct, there is only a one specific heat C, and you can integrate du with regards to temperature if you know the relationship of specific heat with temperature from 1 to 2 in order to find out delta u. And if you don't, you can use the approximation where delta u is approximately equal to C average multiplied by dt, change in temperature. C average is the value of specific heat at the average temperature of T2 and T1. Can you turn off your mic, please? Moving on towards the enthalpy. Moving moving on towards the enthalpy. The enthalpy is defined as H is defined essentially H is defined as U plus PV, and this is the enthalpy equation. So dH or change in enthalpy would essentially be du plus PdV or VdP plus VdP. This is the enthalpy or the equation for change in enthalpy. Now, you know that the specific volume for solids and liquids is essentially constant with regards to pressures. This term would automatically turn to zero and you'll have du plus VdP. Now, once you have this VdP term, you know that du is essentially equivalent to the C average Tt. So you can write approximately delta H is C average delta T plus V delta P. Now, for solids, you essentially have V delta P term, which is very insignificant. Change in specific volume is very small. So the V delta P terms essentially becomes insignificant, and del U equals to they are approximately this del H is equivalent to del U in case of solid, which is approximately equal to C average delta T for solids. For liquids, there are two special cases which are encountered. One is a constant pressure process where pressure is zero, your delta H would essentially be the same as for delta U, or as in the case of solids, and it would be C average delta T. The other is a constant temperature process, as in pumps, in which your delta T is essentially equal to zero and your delta H becomes V delta P. Now, if you remember, for compressed liquids, you have taken this, since you're talking about liquids. For compressed liquids, you said that if the table is not available, you can go for the approximation that for compressed liquid at any pressure temperature can be approximated as HF at the saturation temperature, the enthalpy value of the saturated liquid at that temperature. This approximation can be this is the approximation that you have seen. This is the approximation that you have seen earlier, can be modified with a more accurate uh, relationship where you can add this term V delta P term in addition to this approximation. V delta P is essentially coming from the constant temperature process, and V delta P is essentially what VF, and the difference of the actual temperature given to you minus the P saturation at that temperature. So we'll see one example related to how we can find out the change in enthalpy for a compressed liquid via three methods. One is by using the compressed liquid tables. The other is by approximating it as saturated liquid, which is HF at the given temperature. And the third is where you have to use the correction by adding V delta P term. So the first one is your liquid is at 100 degrees centigrade and your pressure is 15 megapascal. If such is a condition, you will just go to the compressed liquid table at, which is table A7, at 15 megapascal, 100 degrees centigrade. Your enthalpy value is 430.39. It's simple enough from the compressed liquid tables. When you have to approximate it as saturated liquid, you know your temperature is 100 degrees centigrade. So you have to find out the enthalpy value at the saturated liquid enthalpy value at the saturation temperature of 100 degrees centigrade. So you'll go to table A5. In the table A5, you have temperatures, saturation temperatures given to you as 99.97 and 105.97. 100 lies in between. So you'll have to do the interpolation for the H value, where you can find out the HF saturated liquid value at the desired temperature. So 99.97 enthalpy is this, 105.97 enthalpy is this. You have to find out at the saturation temperature of 100 degrees centigrade. You'll do the interpolation and the value comes out to be 419.17. Now this value is basically, if we compare it from the compressed liquid value, it gives you an error of about 2.6%. The third is where you use the approximation of HF at saturation temperature plus V delta T. So you'll add V delta T terms to this approximation to make it a better approximation. V is nothing but VF at the saturation temperature and P delta P is essentially P, which is the actual pressure given to you as 15 megapascal, minus the saturation pressure corresponding to 100 degrees centigrade or the temperature. So the pressure corresponding to this pressure and the Vf is a specific volume which is in between these two volumes. This is Vf at of saturated excuse me, for saturated liquid at 100 degrees centigrade. Now if you plug in the values, this was the initial approximation that you used. This is the Vf at 100 degrees centigrade, Vf at 100 degrees centigrade saturation temperature. This is the pressure which is 15 megapascal given to you, and this is the pressure P at saturation temperature. So this is the saturation pressure at the given temperature. Now you see the answer comes out to be 434.07, which reduces the error from 2.6 to 1%. So this approximation essentially reduces your error in the enthalpy calculation for compressed liquids. Moving on, we'll move on towards the last example. The last example says that you have an iron block of 50 kg at 80 degrees centigrade, which is dropped into an insulated tank that contains 0.5 meter cube of liquid at 25 degrees centigrade. You have to determine the temperature when thermal equilibrium is reached. That means the final temperature or T2, which is common for the water and iron block. Now, if you look at the schematic, if I assume this as my closed system, which is insulated, no heat can flow in and no heat can flow out. Q is essentially zero. Similarly, there is no work done associated with this system, so W is also zero for this system, closed insulated system. I have the energy balance equation which says E in minus E out equals to change in energy of the system. If my system is closed stationary system, I can represent it as delta U. Since no energy is flowing in and no energy is flowing out, I can say that delta U is essentially equivalent to zero. So I can say delta U for my system is essentially equal to zero. Furthermore, since energy is an extensive property, it is dependent upon the mass. I can divide this delta U of my system into two components, delta U of iron and delta U of water. So this whole would combine together to form the total delta energy, delta U of the system. So I can combine delta U of my system as delta U of iron and delta U of water. And delta U for solids and liquids, you know, is C M C dt. This is du. For iron, if I write, it is mass of iron multiplied by specific heat of iron into the temperature difference, T2 minus T1. T2 is the final equilibrium temperature. T1 of iron is 80 degrees centigrade. Mass of iron is known to you. C value you can find out from the tables. Similarly, mass of water you can find out from the volume and density of water, known density of water. C you can find out from the temperature from the tables. T1 is given to you as 25 degrees centigrade and T2 is the same final. If you look at the C values from the mass value, you can divide the volume by the specific volume, which is 1 over density of water or 1 over 1000 kg per meter cube. This would give you the mass of water as 500 kgs. And now if you plug the find out the values of C for iron and water from the tables, it is 0.45 kilojoules per kg for iron and 4.18 kg for water from the table A3. Once you have these values, you can plug it into the equation which we have written for delta U of our two components of our system. And once we plug in the value, mass was known, C of iron was known, T2 was to be found out, T1 for iron is 80 degrees centigrade, similarly mass for water is 500, C value is 4.18, T2 is the final equilibrium temperature, and T1 for water is 25 degrees centigrade. This gives you the final temperature of water as 25.6 degrees centigrade. I hope this is clear. Is there any question regarding this?
No, sir.
All right, so I'll stop over here.